start the actual fun. Okay, so I think, can everybody see that screen? And it says 3 very different stories inspired by Dark. Okay, phenomenal. So, okay, so let me start with the non-math part whatsoever. So during winter break, we were like, oh no, we're locked down in the houses and maybe we should just watch something on Netflix. And then we were like, oh, there's this TV show Dark that some people have recommended. And then we watched it. I think it was a week. Uh, and my husband Donnie was incredibly confused after just 3 days, because if you haven't watched the show, and this is not a spoiler because just like what the show is about, it's essentially is following 3 different time periods and they're all 33 years apart, and you're seeing the same day, the same date on the 3 times period at the same time, kind of. And so all these people are kind of like the grandparents of the people in the present and stuff like that. And so Don is like, I don't know who half these people are because there are 3 actors playing everybody, and I forget what timeline we're in. And I'm like, yeah, this show is good. He's like, well, for someone with a PhD in math. And I'm like, okay, well, in the end, we watched it together till the end. He endured and he enjoyed it a lot. So it's a good show. And I was like, oh, that's wonderful. What if I do a math talk where I'm like just jumping from one year to another, talking about 3 different people who are non-related, but we can pretend that they're the reincarnation of each other or something like that, if you prefer, to make it more interesting, and then be like, oh, wow, crazy. And so I think this is good because it also, I think there's a talk on Friday on the NASC NSC about women in science. And of course, so I guess anecdote time before we start. When I was a grad student, I was talking to my roommate, who was a woman, and she was in several complex variables. I'm an algebraist. And then I said, I was studying for my advanced topics exam. And I said, it's so interesting how the only woman that is mentioned in all of these theorems is Emmy Noether. And she said, yeah, of course, it's interesting, but if you think about it, it's kind of obvious. And I was like, what do you mean? And she's like, well, women were not allowed to get PhDs in math until essentially the 20th century. And I was like, oh, wow, duh. It was so obvious, right? But I had not seen it. So I went and I learned everything I could about Emmy Noether. And then the AMS has this amazing poster, which I think is in the break room where the bagels and cream cheese and donuts used to be on Wednesday, with like women in math from the AMS, and then you see all these amazing women and all that they did, and it's all like 20th century. So, but maybe there were women who were mathematicians before this. It's just, you know, they were not allowed to get PhDs, or they did contributions in math that didn't require a PhD or something like that. So allow me to start. And so we'll start with a joke. So we have Dido, Sofia Kovalevskaya, which is also known as Sonia Kovalevsky, and Maria Chudnovsky. And so these are the 3 women that I'm going to talk about today. And of course, maybe if you know music, you know that this is Dido, the singer, but this is not the Dido that I'm going to talk about. So that's just the joke slide. Okay, so now the real Dido, who, according to what we know, was born in 839 before Christ. But again, her real name apparently was Elisa, but maybe she wasn't even real. So it's a mythical creature, but she's not a myth. Like, there are a lot of actual historical records saying that this person did exist. So that's person number 1. So, and we know when she was born, 839 BC. Then we have Sofia Kovalevskaya, who was born in 1850 in Moscow. And then Maria Chudnovsky, born in 1977 in Leningrad, Russia, also. So these were 127 years apart, and these were, well, I guess 2,689 years apart. So that's fun. She was, oh no, what happened? Man, something happened. These things are out of order. Ah, okay. I guess the slides compress all into one slide. So we'll just jump linearly, I guess. So let's talk about Dido very quickly. She flees Tyre, which is where she was born, in 1825 after her brother Pygmalion, who was the king, murdered her husband, Acervus. So that's intense, I guess, for several reasons. The first one is, if you look at the dates, that means that she was 14. She was already married. Her dad had already died. And now her brother, for some reason, hates her husband and murders him. So yeah, I would also escape this horrifying place no matter what. So she leaves, like, oh no. And of course, she doesn't live by herself. There's people who follow her because she's like, the sister of the king. So maybe if the king dies, she'll become the queen if nobody else is in the line of descendants. But I guess that back then it was harder for that. Like there's always some weird male heir somewhere who is like, oh yeah, doesn't matter. He's like the third cousin twice removed from the king, so he has priority over the actual daughter. Again, 825 BC. So at the same time, we have Sofia Kovalevskaya, who at the age of 18 marries Vladimir Kovalevsky. So this is the great interesting part. She didn't marry him out of love. It's not like, oh, I met you, we're meant for each other. No. So the thing is, Sophia was incredibly good at math. By age 9, her parents had already gotten tutors for her to teach her math, and she already knew she wanted to learn calculus because she had seen pages of calculus books and she found it super interesting. Not only that, but by age 14, she had on her own created all the trigonometric functions and figured out all the trigonometric identities and all the hyperbolic trigonometric functions also, which is crazy, thinking that she wasn't getting an actual formal education. She was just being tutored. And then one day her tutor came, and that's when she showed him all this stuff. And he's like, so you did this on your own? Like, this is not like what it's on the book. She's like, oh yeah, this is like obvious. So he went to talk to her parents, and he's like, okay, so she's gonna be the next Pascal. She's that smart. You have to find a way for her to actually truly study math. And she's not gonna be able to do that here in Russia. So also part of the thing is her sister was a very well-known communist radical in the 1850s. So, but she's like, oh, hey, you know what, Sophia, I have a friend who is at the university. Not that she went to university, the sister, but it's like she's studying paleontology. So, why don't you marry him? And then once he moves out of Russia looking for a job in Europe, you can go with him. And she said, great idea. Like, that's my escape. This is her story of her fleeing, right? So she marries Vladimir, and like I said, that the couple moves to Germany because, like, it's a fake marriage. She's just doing it so that she can escape. So they move to Germany. We stop there. Jump into now Maria Chudnovsky. At some point between 77 and 1996, even 1992 probably, she moves to Israel and she decides to study mathematics. So at the age of 19, she has a bachelor's in math, and then at the age of 22, she has a master's in math. So she's like, great, math is awesome. At this point, there's a complete difference between what's happening to Dido and Sophia versus Maria. Maria hasn't even thought about marrying anyone. She hasn't fled her country trying to learn math, because at this point, women were allowed to go to uh, the university in Russia. She just moves because her parents are actually from Israel, so they decide to move back, and that's it. So she studies there. Great. So now let's go back to the past again, all the way to what's happening with Dido. So now it's 1814 BC. Dido is a little bit older. She's 25. She has been in exile now for 11 years. And she gets to this place in Northern Africa where she meets this King Jarbas. And she very politely says, would it be possible for us to get a piece of land so that we can stay here for a while and, settle the people who escaped tired with me? Like, we've been all over. And he says, yeah, sure, but how much land do you actually want? And Dido is like, as much land as I can encompass with the hide of an ox. And King Jarbas accepts. Of course, as you're about to discover, that was a big mistake because Dido is very smart, and she's just like, oh, let's just murder an ox, and I'll take the hide off, and just whatever I can cover with that or encompass with that, you'll give me. He's like, sure. I'm sold on this. How much can you encompass with an ox hide? So, okay. We move to now the distant, not so distant past. And now that they're in Germany, Sophia goes first to, I think it's Göttingen, and she asks for permission to audit classes. And they let her for a year. So she's going to the university and she's just auditing the classes. She's not getting any credit for anything. But in 1870, she meets Karl Weierstrass, who realizes she really is very smart. She shows him some of her own computations for one of the classes that he's teaching, and she goes to Berlin, where he's at the time, and the University of Berlin doesn't allow her to actually audit the classes. They're like, no, maybe Göttingen will do that. Like, we're not them, so you can't. So Karl Weierstrass tutors her in private. He starts going to where she lives, and he gives her the notes that he uses for his lectures. And she's, learning all this stuff essentially with him and on her own. Great. I mean, not so great because this is awful, but great for her because she's still learning, which is what she wanted. So now we have Maria, who once she completed her master's, she moves to Princeton for graduate studies for her PhD in 1999. And now the story continues. So in 1814 BC, Dido takes that ox hide and founds the city of Carthage. So yeah, crazy, huh? She took that ox hide, cut it really, 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 little pieces, and then she put all the pieces and she encompassed enough space to found the city of Carthage. Yay, go Dido. So there must be some math there. Like, she must have done something with that ox hide involving math. We're about to find out. So now we're with Sophia, and it's 1874. So now she's 24, and she earns a doctorate in mathematics from the University of Göttingen. Because at this point, she has written 3 papers on her own while working with Karl Weierstrass. One of them is on partial differential equations. The other one is on the dynamics of the rings of Saturn. So one of them had to do with physics. And the third one had to do with equilibrium and motion. And so, you know, Carl takes the papers and he's like, well, they need to give you a PhD for this because this is more than that. So Carl essentially fights these people and says she has written 3 papers. This is what she has. You're going to give her a doctorate. She's going to defend it, and you're going to waive all the other requirements. And the university, for some reason, accepts. I guess, like, you don't contradict bias stress. And so they're like, yep, she earned it on her own, right? It's just like they didn't want to give it to her. But he's like, oh, well, you better. Boom. She gets the doctorate. At age 24, like, which is impressive again. And so now we're with Maria, who obtains her PhD in 2003 at age 26, 4 years after being in Princeton. So it seems like things are moving very quick for everybody. So now we get to the end of Dido's story. In 759, Dido burns herself to death. And so that's like a tragic end, horrible. So why did she? Like, at this point, everything was going her way, you would think. She was the queen of Carthage, number one. Her brother had died 8 years before. So now she could go back to Tyre and be like, I also claim this. But here's the thing. At that point, King Jarbas was like, hey, remember that ox hide that I gave you all those years ago? Well, because of that gift, I think that we should marry. So I can also get Carthage. And I mean, you know. And Dido was like, I don't know, maybe I don't like you. And she was, what a lot of historians say is that she had never forgotten her first husband, which again, to me is mind-blowing because she was 14 when he died. And she's had promised to be always faithful to him. So she essentially talks to her sister and says, you know what, we're going to build a funeral pyre. And when that Jarbas come here for the marriage, I'm just going to jump there and burn myself. And that she did.
Sorry, is the year correct? 759 sounds like she would be very old.
Yes, the year is correct. Can you believe it?
Oh,
that I mean, that to me is the craziest part of it all,
yeah.
right? At this point, she's very old, and this guy is like, "Oh, let's get married."
Really? Oh.
And she's like, "Yeah, nope." Or, you know, maybe 795. Now that I think of it, you are correct. Like, she was old, but she wasn't that old.
No,
So
80. 80
yeah,
sounds a bit.
that's correct. She was 80. That's okay. There you are. Now it's correct. Yeah,
Okay.
it was like the oldest woman to ever live.
Yeah.
It was 795. Thank you. Yeah, so
Okay,
795. She's 80, and this guy is like, "Let's get married."
Yeah.
She's like, "No, I'd rather burn myself to death," and she essentially dies. So that's the end. But we're gonna come back to her because, of course, the whole point of why she's important to math is how did she use that ox's hide to found the city of Carthage? There has to be a trick there. So now we go back to Sonia. She gets that doctorate. She's like, I made it. Let's go back to Russia because now her husband has gotten a position there. I think it's essentially what an assistant professor is now. He lasts less than a year in the position because he was a communist and he still had these connections with this communist group, and they're like, we don't want you here. So at this point, Sophia's father dies, and they're in Russia without a possibility of doing anything else. So she essentially says to her husband, you know what, like, maybe we can actually be a couple now. We've been together for so long that at this point, like, you know, we are a couple. So 3 years later, their daughter is born. So, and now we go to Maria, and she obtains her PhD in 2003. And now I'm adding how she obtained it. She proved the strong perfect graph theorem, which was an open problem in graph theory since 1961 with Neil Robertson, Paul Seymour, and Robin Thomas. So yeah, that's also impressive. And then, oh, I guess something's missing. So Maria Chudnovsky eventually got married in 2012, and now she has a son. So happy ending, essentially. Not for Sonia, whose husband committed suicide in 1883. So because of that, she has to leave Russia again. But this time she goes to Sweden, where she gets a visiting position in the University of Stockholm. She becomes the editor of Acta Mathematica. And she's the first woman to become editor of Acta Mathematica. Turns out that while she's there in a visiting position, she founds, and this is the part that I don't really know very well how to explain because I don't do differential equations, but she works on some kind of symmetrical top that is invariant under integration when you rotate it. And that earns her an actual tenure position at the University of Stockholm. And she becomes the first woman to actually get a tenure position as a professor of mathematics in all of history. So, and this happened in 1888. So, of course, I think she dies 3 years later. Like with most of these tragic figures, I would say, in the 19th century, all these mathematicians who worked so hard to get tenure or something, they get it and they died shortly after, or they died right when they get it. Like Niels Heinrich Abel, who also, like, if I'm not mistaken, he died the day before the letter arrived with the, oh yeah, you are offered this position at this place. So it's the 19th century, not kind to mathematicians, I guess. But then again, there were people who were tenured. So I guess Karl Weierstrass is the counterexample. He was there for quite a while and he was able to do good. So the most important thing is, and I think I didn't want to go too in depth with Sonia in this sense, because I think that you're having an AWM talk coming, and the AWM has a day dedicated to Sonia Kovalevsky's day. And so there are many things that are great about it, because she left this imprint of being the first woman to get both a PhD and become a tenure professor. So I guess maybe a round of applause for Sonia in the whole, like, yes, go her. And so, like I said, Maria had a completely different life in that sense. She got married when she wanted. She had a son with someone that she loved, got a PhD at essentially the same age. She's a MacArthur Fellow. She achieved this in 2009. And more importantly, she appeared in a TurboTax commercial. So maybe we should watch it. I say yes, and then we can talk about the math. Okay, so I'm gonna stop sharing, and then I'll just talk about the corresponding maths of Dido and Maria. Now something is wrong with this because it doesn't want to close the present. Okay, there you are. So the other thing that I wanted to mention is Maria Chudnovsky has her own YouTube channel. So if you have taken graph theory, you can go there and you can learn more graph theory on your free time. If you're like, I really want more graph theory in my life. And to that I say, why wouldn't you? So okay, so I'm gonna take my headphones off so that the amazingness of the commercial is very short.
Amy thinks you have to be super.
Okay. And I'm gonna share the screen.
smart to not mess up your tax refund. So we flew in super smart mathematician Maria Chudnovsky to help her.
I have a lot of student loan debt. Can I deduct my interest?
Can Amy deduct your student loan interest?
In her case, yes. The amount goes right here.
In your case, yes. The amount goes right here.
Intuit TurboTax. Taxes done smarter.
So this is funny, but it's also wonderful because, like I mentioned, my first actual understanding different female mathematicians in mathematics was when I saw this AMS poster of women in math. And she is, if I'm not mistaken, the first person to the top right of the poster. So I had already seen this, and this is 2015 when I got my PhD. So I'm finishing my thesis, and my husband is watching TV, and all of a sudden I hear this voice saying, "We flew in Maria Chudnovsky," and I'm like, "What? Where?" So I see the commercial, and I'm like, "Oh, this is hilarious! Ha ha ha! Go Maria!" Of course, this is not an achievement, just like getting her PhD or getting the MacArthur Fellow or getting the $10,000 that she got for solving the strong perfect graph theorem. But hey, she's in a TurboTax commercial, which in a sense is a pinnacle or a pinnacle of what we should all envision at some point. So, of course, that's kind of a joke. But now let's talk the math. Are we ready for it? I am. So, if you Google Dairo's problem, you will discover that this is the whole ox height thing, right? And the question is, what is the largest area that you can encompass by a fixed perimeter? And so this is the part when I'm gonna maybe require some audience participation, but unfortunately math professors are completely forbidden from giving the answer because they all know it. In particular, Jens and Sylvia, who are people who work on this kind of stuff, are absolutely forbidden.
I don't think I can say I know it, but go ahead.
Okay.
We'll see.
If you don't know it, then you can participate. So any guesses? Okay, I'm gonna change the question. What is the triangle with a fixed perimeter that has the largest area? And again, did somebody have the answer? You can just tell me what type of triangle it is.
I'll guess.
Yes.
Equilateral?
That's correct. Yeah, it's an equilateral triangle. Emma, you have gotten the first correct answer of the day, which is great. So, right, an equilateral triangle. There's many problems like this when you do Calc 1, right, in optimization. Of course, actually getting to the equilateral triangle with fixed perimeter is a little bit harder, right? Usually they tell you with fixed perimeter and base this, and then it's a Calc 1 problem. But we can actually answer this one with some Calc 2. and Calc 1. So here's a question. If you have a fixed base, yes, and so what you have is that the other two sides, the addition of them is fixed. Yes? And so say that I have a point and this, and then I have another point that also satisfies that, and then I have another point that also satisfies that. And so if I take all of the points that satisfy that, I can form a triangle with this fixed thing. What shape am I creating?
A semicircle.
Are you sure? Remember, this
Not
is
really.
this is fixed. This addition is constant. There is a particular mathematical shape that satisfies this, and you learn about it in Calc 2. At least I did. Hopefully you did too. A circle is a type of this, I guess.
Is it an ellipse?
That's correct. It's an ellipse. That's a very bad ellipse, but it's an ellipse, right? So now you know that all that's happening is, okay, so okay, I'm really bad at drawing.
And
Okay.
so a circle is when the base has length 0?
That's correct. It's a deformed ellipse.
Right.
Like the two foci become one. That's really what it is. So we have this ellipse. And so obviously in this case, this is just a geometrical problem because what you want is for the height to be the biggest. So it has to be right here, which creates an isosceles triangle. So now that you know that the answer for a fixed base is an isosceles triangle, you can make this again a Calc 1 problem by now making the base vary, knowing what the area is. And that's what you want to maximize. So this, wonderful. And so what happens if we have a quadrilateral? So what do you think is going to be the figure that encompasses the biggest area with a fixed perimeter?
A square.
That is correct. 2 for Emma is a square, right? And so you can also prove this using calculus. It requires more detail because what you want to fix is the length of a diagonal. And then use the fact that what you have then are two triangles on each side. And so it gives you a rhombus, and then you actually get the maximum where the length is precisely a square root of 2 times a fourth of the perimeter. Calc. Yep. So, okay, we get it. This is great. But Dido didn't have calculus back in the day. So probably this whole thing is like, yeah, she couldn't have done all this, but she was very intuitive and she clearly was very smart. So what do you think is the answer for Dido's problem based on these two answers? Okay, Emma got the third one because she made the shape. It's a circle. Ta-da! Right? But the question is, how do we prove it? Right? A spoiler alert, this is what Dido did. She took the oxhide, she cut it into very thin strips, and then she created the semicircle with the coast that she had, and that was the highest area too. And that's how Carthage was founded. Like, again, it's crazy that somebody intuitively knew that a semicircle was the answer and that she figured out how to cut this oxhide in these very tiny strips to get this big semicircle. Again, King Jarbas, you didn't think this through. Like, clearly he didn't have an intuition in mathematics. He shouldn't have agreed to it, but go Dido. So the thing is that this problem is something that is considered the first problem in the theory of the calculus of variations. So how do we solve it in general? How do we actually prove that it's a circle? Well, it's kind of funny. You have, say that you have this curve, right? And of course, we're assuming that it's smooth, because if it's not smooth, things are not nice. But there's a way of actually proving that smoothness is what you really want based on all these other things that I have said before. And so if you have this, you can parameterize the curve. Yes? And if you parameterize it, then you can compute. What can you compute? Regarding the perimeter. Can you compute the perimeter? Is there a way of computing the perimeter of a parameterized object? This is a Calc 3 question.
And if you're in PDs, you should know these.
Oh, ta, put you on the spot.
Line integral?
Okay, yeah, that's correct. Which line integral?
Oh, you asked me which?
Yeah. It's okay. I won't put you on the spot unless you want to answer.
It's the one with the square root of squared plus partial squared plus partial squared. I forgot. I don't know the exact formula.
Okay, but you're correct.
Something with ds, yeah.
Yeah, there you are with ds, right? Because what you want is to find, so you have this, there's a tangent vector, right? And so I wonder, can anybody give me the tangent vector in terms of x and y?
The gradient.
Okay, yeah, it's x prime t, y prime t, right? So that's what we want. So we got the tangent vector, and you multiply. So the length of the tangent vector, and you do the s, so that it's not the whole vector, but it's just like, like the small direction, and you do that over the parametrization. Yep. And this has to be the perimeter, yes? So question number 2, can you find this area? Maybe there's something from Calc 3 that also tells you how to find the area. I'm gonna tell you so that nobody suffers anymore. Green's theorem, yes? Because Green's theorem relates the area enclosed with some line integral of the, right? So we win. Like, now we have something that involves derivatives, and we can solve it. And when you solve it, you get that it's a circle. I'm not gonna solve it because I have 5 more minutes, and I want to talk about Chudnovsky. Was this fun? Go Dido, who didn't know calculus of variations and solved the problem on her own. You need a special type of ability for that. So now let's talk quickly about graph theory, which is fascinating and it's amazing. So I'm gonna draw a graph. It's one of those graphs that I love drawing, and then people are like, what kind of Satanist are you? And I'm like, no kind. This is just a famous graph. It's actually a forbidden graph in many situations. This is called K5, the complete graph in 5 vertices. Okay, so essentially a graph has something that is called a graph G has a chromatic number, and it has something that is called the clique number. Okay, so this is the smallest amount of colors needed so that every vertex is assigned a color, and not two vertices connected by an edge are the same color. Yes? So in this case, the answer for this graph is 5. Because everybody is connected with everybody, so everybody must be a different color. Okay? So now the click number is the highest number of vertices such that all the vertices are connected to each other. So in the case of K5, the answer is 5 also. Yes? So this graph is what we call well, it's not perfect yet. This graph has this amazing property. The click number and the chromatic number are the same. Yes? So now here's the definition. A graph is perfect if for a graph G is perfect, is for all induced subgraphs, and I'm going to tell you what induced is. G prime, the chromatic number of G prime is equal to the chromatic number of G prime. So this property of chromatic and click being equal is true not just for the full graph, but for every induced subgraph. So an induced subgraph is when you take some vertices, say those 3, you keep them and you keep all connections between them. So every complete graph is perfect. Because if you take any subset, you're gonna get a complete graph that is smaller. So this is like the very obvious example of something that is perfect. But maybe at this point you're like, I don't know, I don't think that things that are not perfect exist. But I'm gonna give you an example. So let's forget K5, and we're gonna use something that is called C5, where you simply have 5 vertices all connected. And so the chromatic number is 3. Because if you start with a vertex, then the next vertex has to be a different color. Then the next vertex better be 1, because otherwise you're using 3. So the next one has to be 2, and oh no, the 5th one has to be 3. But the click number is just 2. Because no matter what you choose, it's just 2 vertices that are connected, right? So this thing, not perfect. Yes? Okay, so the strong perfect graph theorem essentially was, is there a way to characterize perfect graphs? Like, you know, is there an if and only if way of saying that a graph is perfect? And somebody made a conjecture, which they proved. And this is the thing. A graph is perfect if and only if neither the graph nor its complement have an odd cycle of length 5 or more as an induced subgraph. So essentially, neither the graph nor the complement can have a 5-cycle or a 7-cycle or a 9-cycle as an induced subgraph. And this took 42 years to be proven.
And is it much quicker to verify that property?
What do you mean? Oh, that it doesn't have the, yes, it's quicker.
Okay, yeah,
It's considerably quicker.
that's what I was wondering. Yeah.
And when I say considerably, so the Ramsey theory, right? When you try to compute the number of clicks with colors of things with 43 vertices, it takes more time if you're assuming that there's one computation done per microsecond than the time that the universe has existed.
Mhm.
So, no, it's bad to do those click things.
Yeah.
So, and that's it. Thanks everybody for coming.
Yeah, thank you. It's very entertaining. I have no intuition about graphs, so I can't tell what is faster, but I trust you.
Induced subgraphs are very easy to compute.
Okay.
And in fact, there are algebraic methods that allow you to do things with the graph that tell you that.
Okay.
And
Yep.
that makes it
All
even
right.
faster.
Yep. Thank you.
No, you're welcome.
Well, I have a meeting soon, but it was very good. Thank you, Gabriel.
Thanks
Bye.
for coming.
See you, everybody.
Yeah, and also thanks to Chris and Isabel for organizing this.
Yes.
I appreciate that. I gotta run too.
Nice seeing you.
Yeah, likewise. Bye-bye.
Bye.
Professor, I don't have a question, but I have learned about Dido. Like I took Latin for a really long time, and so I read the Aeneid. I know all about Dido, and I've never considered her like a math figure. Like we always would kind of just brush over and be like, oh, she's so clever for like turning it into a thread or really thin strips or whatever she did and encircling Carthage like that. But I never considered it as a like really just an optimization problem for how to get the most land underneath that oxide. But that was a really neat comparison. So thank you for bringing that in. That was really cool.
Oh, no problem. I mean, we're a liberal arts institution, right? So thank you for bringing up the Aeneid. That's where that's what I'm saying. Like, did she really exist? I think he just changed some names there and essentially took this historical record and put it in the book. And it's like, oh, look at this, so cool. And it's like, oh, horrifying.
Do you know why they call those perfect graphs perfect? I mean, what's the origin of that name and why do people continue to use it? Because perfect can mean lots of things, right? So what's the...
I guess it's because the click number and the chromatic number were two of the invariants of a graph that were the most studied at that point. And so they were like, like having a graph that actually satisfies this equality for every induced subgraph. It's the holy grail of graphs.
Like the circle for shape.
Like the circle as a shape. So that was also part of the joke in the connection. It's not only this, but any sub part is regular in a sense. That's how I see that idea. But yeah, I think that we talked about this in one of these history of math series in one of these Quanta Magazine's articles, or maybe it was during Ben Orleans' visit. Somebody mentioned Quanta Magazine. And Quanta Magazine, like every year, publishes a big result about graph theory that was just finished. And it always has to do with some kind of coloring scheme, or because the open problems in there are so many. and they are all still open, except of course the ones that are being solved every year, but they're not easy. And it's always somebody who comes up with a very clever new way of understanding the graph, or putting some algebra into it, or using hyperreals, which I think is the last one that I read, and I was like, okay, I've seen it all.
And for those of you in PDEs, since we mentioned that earlier, often you take a PDE in order to solve it. If it's nonlinear, then you use a computer. And you take space, which is continuous, and you divide it up into little regions. And if you look at the edges and the corners of those regions, those are the vertices and edges of a graph. And so it turns out that the graph theory stuff applies to PDEs too.
Math, connecting everything. That's thank you, Dan, for that. I think that that's like my favorite. When I hear those things, I get so happy, because I'm like, everything really connects. It's
And it flips around, right? Because sometimes to solve the graph theory problem, you need to extend it to a continuous system and look at some zeta function or something.
which is why I mentioned this hyperreal stuff. That's essentially what they did. So that's why I'm like, yeah, it's math is beautiful. Period. Like, you don't have to, not up to debate. But thank you for having me, Chris and Isabel, and thanks everybody for coming again and for participating.